Hi everyone, I'm Negar Nida, a third-year PhD candidate at NYU working with Professor Brandon Regan, and here I want to present our work CiFlow, a data flow analysis and optimization of key switching for homomorphic encryption. This research was accepted in ISPASS 2024, and we show that how strategically scheduling the instructions will help us to save on-chip memory and also save up to 8 times off-chip bandwidth. But let's start with this question that why do we need privacy? Well, a simple example for this is that these days people put a lot of their personal information on social media, where this information are gathered by companies that do computation on this information and provide some free services like advertisements for the user. But the problem is that the user has no control over their data, how and where this data is being used. So how can we solve this problem and protect the data? A solution for that is to use fully homomorphic encryption. But let's see how homomorphic encryption is solving this problem. As we mentioned, we have a user that has an application, and then there's a server that does some computation. Here, the user encrypts the information and sends it over to the server, and by using homomorphic encryption, the server is able to do computation on encrypted data without the need to decrypt them. So the server will generate some encrypted results. It will send it to the user, where the user is the only one that can decrypt this information using the key. But definitely doing secure computation has some trade-off, and that's high latency and high energy consumption because of doing computation on encrypted data instead of actual data. But when we deep dive into the homomorphic encryption algorithm, we find this workload named key switching that looks to be the bottleneck of homomorphic encryption. What's key switching and where it has been used? So in homomorphic encryption, we have a ciphertext that encrypts a message M under a key S. Whenever we do rotation or ciphertext multiplication, we end up with another ciphertext that's now encrypted under a different key S prime. But the problem is that the user can only decrypt information that are encrypted under the initial key S. So here comes key switching that converts this ciphertext to another ciphertext that now is encrypted under the initial key S. But if you look into the inference of ResNet 20, there's around 7K rotation in ciphertext multiplication, and we need to do key switching after each of these operations. And looking into the runtime, around 70% of homomorphic encryption inference is only occupied by key switching. In addition to the runtime, key switching requires some evaluation keys for the computation that can be up to 500 megabytes. Many of previous research have decided to put these keys on chip, but then the problem is that you would need a really big on-chip memory. And another way to solve this is to put them off-chip, stream them on-chip, but then you would need a big off-chip bandwidth. So this is an important workload. It's taking a huge amount of time. It has a lot of data. It's worth to focus on. And there have been lots of variations to key switching, and one of the high-performance key switching algorithms is named hybrid key switching, or HKS. And in CiFlow, we will focus on HKS and how to optimize its data flow to save on-chip memory and off-chip bandwidth. In this presentation, I will introduce the hybrid key switch data flow, the methodology of our research, and finally, we will do evaluations on RPU, which was our previous paper accepted in ISPASS'23. Let's start with how the data looks like in homomorphic encryption. So the input in homomorphic encryption is it's like an array that has a polynomial degree of 2 to the 17, or it's an array with 2 to the 17 elements, where the size of each of these elements can be up to 4 kilobits. Well, this is a really big input. So what they do is that they use residue number system, or RNS, to convert this big polynomial into smaller polynomials, and they will call each of these small polynomials a tower or a limb. And the structure of each of these towers will have the same polynomial degree as the input. It still has 2 to the 17 elements, but now the size of each of these elements is only 64-bit. One of the optimizations that hybrid key switch does is that it groups sequential towers together and processes them separately. Each group of these towers I'll call the digit, and we will use this term digit in the next slides. An example of homomorphic encryption operations is a ciphertext multiplication, where we multiply two ciphertexts. Each of these ciphertexts have two components, and the structure of each of these components is the same as the big polynomial that we just showed you. And the result would be a ciphertext with three components, where each of these components have the same data structure. And two of these components will be the input to the hybrid key switching algorithm. Now I will show how the hybrid key switch algorithm actually looks like. So one of those components is going to be the main input to the HKS, and the other will be used for a simple vector-vector add. Each of these small rectangles here will be a tower that we just showed in the previous slide. It has 130K elements, each element 64-bit. And then in this example, we're breaking down the input polynomial into 3 digits, and the computations are going to be done in each digit separately. Then the workloads of hybrid key switch, you see we have inverse NTT that you have to do it for all of the input towers. And then we have bconf that's extending the size of the input. It's increasing the number of towers inside each digit. And then we have to do NTT on the output of this. And then we have a vector-vector multiply that multiplies the output with the evaluation keys. And finally, we have to add the result of all the digits to calculate the final result. The second part of the hybrid key switch is almost the same as the first part, so I will focus on the first part, and all of the terminologies that we apply here can also be applied to the second part of HKS. So now I will introduce the data flows that we have presented in CiFlow, and we will start with the first data flow called max parallel. Here in max parallel, each tower is loaded onto the chip for a single operation, and an operation is computed on all input towers before moving to the next operation. So it's basically ignoring the HKS digit-based optimization. It does inverse NTT on all of the input towers. Then we do bconf, and as you can see, when I'm doing bconf, I'm extending the size of my input, meaning I'm generating a huge amount of intermediate data. That I need to do NTT on this data, and then I have to multiply them with the key, add them together to calculate the output. If we want to prevent going on and off chip in max parallel, we would need around 700 megabytes of on-chip memory. The reason is that, as you can see in P2, for each digit, I'm extending the size of my input, and I need to keep these data on chip for the next step that I want to do NTT on them. Also in P5, I'm generating partial products of the output that I need to keep them on chip so I can add them together. So in max parallel, we need around 700 megabytes on-chip memory, which is a lot. And now we present the next data flow called digit-centric. As the name suggests, in this data flow, each digit is loaded onto the chip, and all of the possible calculations are done before moving to the next digit. So I will finish the first digit, then I will move to the next one, and then I will add the results of each digit together and calculate the final output. This will increase the data reuse compared to max parallel, but still, if we want to prevent going on and off chip, we need around 255 megabytes. And the reason is that still in P2, I'm still extending the size of my input. I'm still generating more intermediate data. And in P5, after I'm done with each digit, I'm calculating a partial product that can either be on chip for final reduction, or I can put it back off chip to save on-chip memory. Finally, we propose output-centric data flow, which is the main contribution of our paper, and it's optimized for data movement and on-chip storage. The goal here is to generate one output tower at a time. And the reason is that when we look into the hybrid key switch algorithm, we realize that for generating one output tower, I do not need to generate all of those huge amount of intermediate data. Only a part of that intermediate data would be enough, and I wouldn't need those generated data for the next operations. So we break down the output centric into two parts. Section 1, we're generating output towers that have the same modules as the input. And here, one digit will bypass P1, P2, and P3, and we will only need one tower from this digit. The rest of the digits need to go through these stages, but the point here is that in bconv, I'm only generating one tower per digit. And that's because that's the only intermediate data I need for one output tower. The other part is called section 2, where I'm calculating towers that have different modules from the input. Here, all of the digits need to go through P1, P2, and P3, but again, I'm still generating one tower in P2. For section 1, this feature gives us the opportunity to require less input on chip, and the inverse entity of all of the digits will be calculated in section 1. And when we move to section 2, the inverse entity of 2 digits are already on chip, and then we can reuse them for section 2. Now we will show what are the operations, what are the sequence of instructions in section 1. So as we mentioned, 2-digit will go through, will be loaded on chip, and only one tower from the left digit will be on chip, and it will bypass P1, P2, and P3. So these 2 digits will go through inverse NTT, we will do bconv, we will generate one tower, and then we will multiply one tower per digit with the key, add them together for the final output. Here, if we want to prevent data movement, we only need 34 megabytes on-chip memory. And the reason is that, as I mentioned in P2, we're not extending the size of our input anymore. We're only generating one tower per digit. And then in P5, we have 2 towers per digit that we can easily store on-chip. So output-centric only needs 34 megabyte on-chip memory. That's 94% less than max parallel. Now I will introduce the methodology of our research. So we evaluated these introduced data flows on RPU, the ring processing unit, which is a vector processor optimized for ring-based algorithms that also includes homomorphic encryptions. This design has 3 distinct queues: ALU queue, load store queue, and shuffle queue. And the shuffle queue is added to optimize the NTT implementation. And these 3 distinct queues allows us to fetch independent instructions in parallel, as long as there's no dependency between them. The functional units in RPU are called HPLE, which stands for High Performance Logarithmic Word Engine. Inside each HPLE, there's a 64-bit multiplier, an adder, a subtractor, and a comparator. We break down the vector data memory into 128 banks. The vector length is 1K, and the size of our on-chip SRAM has 2 configurations, 392 or 32 megabytes. And in the next slide, I will describe why we picked 392 as our on-chip memory. And finally, we provide 128-bit security using proper homomorphic encryption parameters coming from previous research, BTS, ARC, and DPRIVE is our own benchmark. And we also have a software framework that we define 2 distinct tasks, memory tasks and compute tasks, and we define the dependency between memory, compute, and compute tasks. Now let's evaluate all of these benchmarks using the 3 introduced data flows on RPU. So our first configuration is having 392 megabytes on-chip SRAM. 32 megabytes is dedicated for the data and the intermediate data, and the rest of that is enough to store the largest evaluation keys on chip. The baseline here is a max parallel implementation using 64 gigabytes per second DDR5 off-chip bandwidth, and what we want to show is that if we're going to use output-centric, how much bandwidth we can save to get the same performance as our baseline. So here you can see the hybrid key switch runtime using different bandwidths for output-centric and max parallel. The reason we don't have digit-centric here is that BTS1 only has one digit, so the max parallel and the digit-centric implementation would be the same. This is our baseline, and this bandwidth is where output-centric is getting the same performance as the baseline. The difference between these two bandwidths will be the amount of bandwidth saving that we have, and the difference between output-centric and max parallel runtime in the calculated bandwidth will be our speedup. We do this evaluations on all of the benchmarks that we have, and the result is that we can save up to 8 times bandwidth and get up to 4 times speedup by using output-centric. We get these numbers from ARC, and the reason is that ARC had more digits compared to the rest of the benchmarks, and as you have more digits, you're generating more intermediate data, you require more data movement, and the result is that as we have more digits, output-centric will benefit more compared to max parallel. Our next configuration is having only 32 megabytes on-chip memory for data and intermediate data, and streaming keys from off-chip to on-chip. And the reason is that the keys are only used once. It's the data and the intermediate data that might be reused. So this plot is showing the hybrid key switch runtime on different bandwidths while we have keys off-chip. And here, the dotted lines represent the runtime with preloaded evaluation keys on-chip. As you can see, the trend is the same. There's only a shift in the absolute values, and that's because we're putting more pressure on the bandwidth. We're dedicating a part of our bandwidth for keys to be streamed on-chip. So if we used to get the same performance as the baseline with 8 gigabytes per second, now we need a slightly more higher bandwidth to get the same performance. The takeaway of this results was that we can save 12 times on-chip SRAM and with at most 3 times more bandwidth for the same performance. So in CiFlow, we showed that by having keys on chip, we can get up to 4 times speed up compared to max parallel implementation. And then we can stream the keys on chip and save 12 times on chip SRAM with a minor increase in the required bandwidth. Another evaluation that we did was increasing the computational throughput called the modular operations per seconds, or MOD-OPS, to show a better balance between bandwidth and the MOD-OPS. Well, there have been a lot of work on hardware accelerators for homomorphic encryption. A recent work was MAD, and MAD presents a data flow which is similar to digit-centric. And what we showed in CiFlow is that the output-centric strategy improves digit-centric by up to 2.5 times speed up. And MAD can also benefit from using the output-centric data flow. There are also Crater Lake, BTS Arc that introduce a hardware accelerator for homomorphic encryption. They all have large on-chip memory and high off-chip bandwidth, and they can also benefit from the output-centric data flow as well. So in CiFlow, we present a taxonomy and analysis of hybrid key switch data flow. While this is a missing discussion in recent papers, they focus mostly on inverse NTT, NTT optimization, and bootstrapping, while as you saw, inside key switching, we have NTT, and also after each bootstrapping, we have to do key switching. So this was also an important workload to focus on. We showed that by using the output-centric data flow, we can reduce off-chip data movement by increasing data reuse. And the lessons of CiFlow are relatively independent of the architecture and can be applied to any of the previous or next works on homomorphic encryption. And our results show that by having a big on-chip memory and storing the keys on-chip, we can save up to 8 times bandwidth by using output-centric compared to the max parallel implementation. Or we can save 12 times on-chip memory, go to a smaller on-chip memory, and still get the same performance as the baseline by saving 3.3 times off-chip bandwidth. Thanks for your attention, and I look forward to answer your questions.